All right, so on the final set of videos for this unit, all right, we're going to keep talking about limits in the next unit, but this will kind of get us to one good stopping point. All right, so in this one, we're talk about the squeeze theorem and just start kind of combining all this other stuff we've talked about with limits. All right, so the first thing is the squeeze theorem. All right, so the limit laws we work for, we know they work really well for polynomials and they work really well for rationals. All right, however, they don't work well for trigonometric, exponential, and logarithmic functions. And we'll kind of figure out more about how to do those functions as we progress. But particularly with trigonometric functions, all right, we can't like move a limit into a sine or divide by cosine or any of this stuff. So we need to figure out another way we can evaluate some of these limits algebraically. And the way we're going to do that is the squeeze theorem. All right, so again, I broke the theorem up into kind of smaller chunks, so we'll go piece by piece. All right, so first of all, we have these three separate functions, f, g, and h. All right, g is actually the one that we care about. This is actually the one that we're looking to find the limit for. But we know something about g. We know g is always going to be bigger than some function, and g is always going to be less than some different function. All right, so that's our starting point. We have g kind of in between these two other functions all the time. All right, the next step says, if we're trying to look at the limit of all of these functions, again, g is actually the answer we care about, but if we know f, the limit for f goes to this value L, and the limit for h goes to that same value L, then the only thing that's possible is since g is wedged between them, well, if they're touching each other, g has to be in the exact same place. All right, so that's why it's called the squeeze theorem, and we'll see a picture in a second, because f and h are above and below, and they squeeze together and kind of pinch g between them at this one place. All right, so here's the picture. Again, f, this kind of orange line, is always below g. H is always above g, but you can see as we get close to our a value here, f and h create this funnel, and g, since it's getting squeezed in this funnel, has no choice but to be in the exact same place as f and h at that point. All right, so the squeeze theorem, it's actually a really good name for a theorem. Most theorems don't have good names. You're squeezing the function you care about in between two easier functions. In this picture, it's not great because we don't know much about h and f, but we'll do it in practice. The f and h function will be really simple functions. G maybe not, but that'll help us figure out this more complex limit. All right, so x times cosine of x as x approaches 0. All right, we can't plug in just 0 straight away because it's not a polynomial because there's a cosine involved. But one good thing we know about our trig functions is cosine will never be below -1. It's always above -1. All right, our cosine wave just does this. All right, it's always -1 down there. And at the top, it's always below 1. So we know cosine is always going to be below -1, or sorry, above -1 and below 1. All right, well, that's just the cosine function. We're talking about x cosine. So if we do the same thing for x cosine, basically just multiplying everything by x. All right, so x cosine of x is squeezed between -x and x. And then for -x, the limit x approaches 0 of -x, well, that's a polynomial. I just get 0. Same thing for the limit of positive x. That's just the polynomial, so you plug in 0. So these two things that it's getting wedged between both end up hitting 0, which means this answer is also 0. And this is generally how the squeeze theorem will go. It'll use the fact that a trig function is bigger than -1, smaller than 1. It'll kind of simplify the problem by just doing basically the limits without the trig function, kind of like we did. And if those two answers are the same, we know our limit is squeezed in between, we get the same answer. I will do one more. Again, we saw before sine of 1 over x is a really weird limit. It has that oscillation in it, which means the limit doesn't exist. But let's see what we get for x squared sine of 1 over x. Again, it doesn't matter what sine is. Sine of anything always has to be below 1 and above -1. So sine of 8x, sine of 1 over x, sine of whatever, never gets bigger than 1, never gets smaller than -1. So for our function, we know that -x squared is going to be less than x squared sine of 1 over x, which has to always be less than x squared. Because that sine part, again, is always above -1 or below +1. And then we figure out our limits of those simpler functions. Again, they're polynomials, so they're going to be pretty simple. We just plug in again. And this isn't always the case, but just like the last one, we end up getting 0 as our final answer. All right, so one thing you do, graph this function and kind of confirm that 0 is, actually graph all 3 of these functions and see how they kind of squeeze at x equals 0, and you'll see why this is happening. Right, the two parabolas kind of squeeze that function in the middle. But this is the squeeze theorem, kind of the last way that we're going to discuss for the foreseeable future. I will learn another way to find limits in kind of unit 4, maybe unit 5. But for right now, this is kind of all the ways we have to find limits, squeeze theorem kind of being the last resort at this point.